Real exam questions. Question 31, it's about beam design. A beam subjected to frost and rain has a width of 200 millimeters. The concrete quality is C3037 and the steel quality B500. The effective span of the beam is 5 meters. The characteristic value of uniform distributed load, the uniform distributed permanent load on the beam is 7 kilonewton per meter, excluding the self-weight of the beam, and the mobile load has a characteristic value of 10 kilonewton per meter. Determine the height of the beam and the tensile reinforcement, number and diameters, for optimal use of the materials. The stirrup diameter is 10 millimeter and determine the beam height to an accuracy of 5 millimeters. First, we start what we know. We have the beam loaded with a mobile load of 10 kilonewton per meter. The permanent load is 7 kilonewton per meter plus the self-weight of the beam. But this is, we know the beam is 0.3 meter width. And the height of the depth of the beam is not known yet. So the depth of the beam in this formula is expressed in millimeters. That's why we divide in 1,000. From the beam, what we know is the width, and we know the tensile reinforcement. We ignore the compression reinforcement, and we are looking for the total depth of the beam. The diameter of the stirrup is 10. The steel quality is 500 megapascal, and the compressive strength of the concrete is 30 megapascal. We also know that we have to determine the height or the depth of the beam by using optimal use of the material. It means that the maximum strain of concrete must be reached and the maximum strain of the reinforcement. This strain diagram is in domain 2A, and in domain 2A, the full parabolic and rectangular section of the concrete compression stress is reached. So the filling coefficient is 0.81, and the position of the compression force in the concrete is situated at 0.416 times A. So 3.5%, 3.5 per mil and 10 per mil is the ultimate strain in the two materials. The design value of the concrete compression stress is equal to 0.85 times 30 divided by the material factor 1.5, which gives you 70 megapascal. And the optimum depth is then given by this the formula 2.31 times the square root of bending moment divided by the width and the design value of the concrete compressive stress. So D is a function of MD in this example. We know that the beam is subjected to rain and frost, so it means that we have XC4 and XF1 for this beam. According to the Belgium application document, it is EE3, the environmental class. So it means that the needed concrete cover to reach a proper durability, that the minimum concrete cover must be at least 40 or 15 millimeters plus the largest diameter that you will use in the beam. So we gamble that the largest diameter for tension reinforcement is 20. So we take C, a concrete cover equal to 40 millimeters. The total depth is then the effective depth plus the diameter of the stirrup plus the point of gravity of the tension reinforcement and plus the concrete cover C, which is 40. We can substitute for the variables that we know, and we see that we have H in function only of the bending moment. In this formula, the bending moment is given in kilonewton meter because we multiply by 10 to the power 6, and H is given in this formula by in millimeters. We already got from the previous slide that H should also equal to this. We know that QD, the design value of the total load, is 1.35 times the permanent load plus 1.5 times the mobile load, and it gives you an equation in function of H. In this equation, H is in millimeters and QD is expressed in kilonewton per meter. The bending moment, it's a simply supported beam. So the maximum bending moment is in the middle of the span and is equal to the load times span squared divided by 8, and is also then a function of H, the total depth of the beam. So now we have two equations, and from those two equations we can directly calculate the needed depth, which is 426 millimeters, but to an accuracy of 5 millimeters, so it means we will take 425 millimeters. And D is then H minus 60 is 365 millimeters. Then we can calculate the total load, which is 27.32 kilonewton per meter. The maximum bending moment is then 85.38 kilonewton meter. And the needed reinforcement, because we are working at optimum height, then the zeta, we know that, is then 0.892. So MD, you have to express it in Newton and millimeter, and we arrive at 603 square millimeters. So 2 diameters 20 is 628 square millimeters, so that will be okay. Now, just a remark about the total needed depth. We rounded it off to the near 5 millimeters, but be careful because it still has to fulfill the condition that it should be H optimum. So this is a small difference. Now we look at the provided reinforcement. This is also a little bit more than the needed reinforcement. So we are sure that this will be fine. And check off the width of the beam. So the width was 200. And 200 must be bigger than, of course, the concrete cover and the stirrup size of the stirrups times 2, left and right, plus 2 times the diameter 20, and the clear distance between the two bars, reinforcement bars, is 40 millimeters. So we need 180, but the beam is 200, so that is okay. So to summarize, the effective depth of the beam is 365 millimeters. The total design load is 27.32 kilonewton per meter. The concrete cover is 40 millimeters. Total depth of the beam is 425 millimeters. And the design bending moment is 85 kilonewton meter. And the calculated reinforcement is 603 square millimeters. And the placed reinforcement is 2 diameter 20, which gives you 628 square millimeters.